Hi, everybody. So then this is yet another application of linear algebra, and specifically, in this case, linear combinations. And of course, it's linear systems too, because those are tightly connected concepts. This is called finite linear games. So in order to do so, though, I need to prep you a little bit. You need to have a small introduction to what we call modular arithmetic. So if you're given a prime, the set Z sub P, it's the set of all integers from 0 up to and including P minus 1. That's called the set of integers modulo P. Now this is actually, you can do modulo any positive integer. You want to do it modulo 4, 5, 10, you can. It's just primes have an additional extra little feature that we're going to use. All computations done in this particular set, whenever you're done the computation, you don't return that computation. What you return is the remainder of that when you divide it by the P, in this case, the prime. So for example, in Z3, the only elements are 0, 1, and 2. So if I were to take 1 plus 1, I get 2. If I take 0 plus 2, I get 2. But if I take 2 plus 2, that'd be 4, but there is no 4 in the set. I only have 0, 1, and 2. So to find the answer, 2 plus 2 would be 4, but I respond the remainder when I take 4 divided by 3. So then 2 plus 2 is 1. For the same reason, if I were to take 1 plus 2, you should get 3, but that's not what you can get in this particular set. The only answers are 0, 1, and 2. So 1 plus 2 would then equal 3. I divide by 3, the remainder is 0. So 1 plus 2 is 0. Interesting, right? So what I've done for you here is I've included an addition table for you and a multiplication table. And you should be able to do some basic computations. So if I were to say, hey, what is 1 plus 2? That would then equal to 0 in this world. If I were to take 2 times 2, that would then be equal to 4, which is 1. That's weird, isn't it? That means if I want to solve an equation, let's say x plus 1 equals 2 in this world, I would want to undo 1, but there is no minus 1. There is no such thing as minus 1 in this world. It's only 0, 1, and 2. So I want to add something to 1 to make it be 0. That would be, I would take that 1 and I would add 2 on both sides. Because then this is actually 0. 1 plus 2 is 0. So the left-hand side is x, and the right-hand side is 2 plus 2, which is 1 in this world. That's it. That's the answer. A little weird, right? A little weird. Let's try one more. What if I want to solve the equation 2x is equal to 1? Again, in this particular world. You can't divide by 2. There is no division by 2. There's only addition multiplication. There's no division by 2. Instead, what I want is I want to multiply 2 by something so that I get a 1. So I have 1 times x in the end. So I will multiply both sides of this equation by 2. Weird, right? Then this 2 times 2 is 4, which is actually 1. So this is 1 times x, which is x. And that would then equal 2 times 1, which is 2. And that's the answer. That's the solution to that particular equation. Okay, with that very simple, basic get up, we could then talk about linear games. In linear games, we use vectors from ZP, like Z2, Z3, Z4. So then the dimension of the vector is a superscript. So something like if I were to write the notation Z3 with a 5 here, that means it's a vector with 5 entries, 1, 2, 3, 4, 5, and all the entries are 0, 1, or 2. It's one of those numbers. And we do all vector multiplication, all scalar multiplication, but with us using the set ZP to do everything. So everything, therefore, in this world will be modulo 3. Now, the nice thing about this world, about this type of new set of vectors, is it actually has all the properties of vectors. Remember those main 8 properties? This new thing actually still has all those 8 properties. So everything I've done relies just on those 8 properties. Everything. What the objects actually were didn't matter. It was the properties that allowed us to form linear combinations and to manipulate those linear combinations. Okay, with that in mind, this is called the light switch game. It's an example of a finite a finite game, one of these finite games, finite linear games. So imagine that underneath each of these light bulbs is a button. If you push the button, it changes the light status of the light directly above it, but then also the lights adjacent to it. So if I were to push A, by pushing A, I would light right now A and B. But if I push B, as I push D, it would then change lights C, D, and E. If now in this state, if I were now to also touch button C, what would happen is B status would change, it would turn on. C and D status would change, they would go off. E status would not change, it would stay on. So if I push D and then C, the only lights on would be B and E. So the question then is, what if we start with this particular arrangement? The lights B and D are currently on. What I want to know is what buttons to push and what order, how many to push. So in the end, everything's lit. Can it even be done? Well, in a game like this, you should notice that the on-off light status and the press, don't press status of the buttons are all binary. It's either this or that. So it seems then what we should do is think of this as a finite linear game, but where we're doing all computations modulo 2. So I'm going to do everything in terms of vectors from V2 superscript 5. So Z2 superscript 5. Okay, first I need to show you how to represent the current status of the lights. So we'll use a vector for that. So we'll call that S for current initial status. It'll be a vector, 5 entries. Every single entry will be either a 0 or a 1. 0 means that light's on. So 0 means the light's off. 1 means the light's on. So I've given you a certain initial status, and I've given you the current lights that go with it. So you can see how they connect to each other. Also, we can then use vectors from Z to 5 to represent lights being toggled when a button is pressed. So we'll have a vector for button A, we'll have a vector for button B, and so on. So I'll use for button A, I'll use the vector called little a, and so on. So then for a vector, if you go and have an entry, that means you change that particular light status. So if I push, for example, button A, it only changes the light status for A and B. So then the first 2 entries for vector A will be 1s. The other entries will all be 0s. One more time, if you look at button D, it will change when you push it. It will change the light status of C, D, and E. So D will be a vector where the first 2 entries are 0 because button D doesn't affect those lights. But the last 3 entries are all 1 because button D will change the light status for C, D, and E. Okay. Now, how to go about using these vectors? Notice what we can do is if you give me an initial light status, in this case, S, like I gave you, and then you push one of the buttons, like in my case, I'm pushing A, you would go from the light status you see where B and D are lit, and after pushing A, you'll now have A and D are lit. But in terms of vectors, you can denote the resulting light status by taking the vector S and adding to it the vector A. Because when you add those 2 vectors together, remember you're doing everything modulo 2, the vectors add together, but anytime you have 1 plus 1, there is no 2. That would be 0. So the 2 vectors, as you can see, the vector sum actually does in the end give you the correct light status. So that means we can represent pushing buttons by just adding vectors. That's great. So that means then, what if I start with initial state S and I just start pushing buttons willy-nilly? So I'll push A, then C, then D, then A again, then E, and then C. That would then be this vector. This would then correspond to the final light status. There's something that's interesting here, though. Remember that these vectors, though, come from Z25. And in that case, we still have all the properties, all those main 8 properties. So I can reorganize and reassociate and commute and collect. Because of that, these vectors all add up to be that. Now, the reason that's interesting is that notice I have 2 times a vector. if you remember what I gave you before, if you have 0 and 1, but if you multiply those numbers by 2, you either get 0 or 2. But if you do that modulo 2, you get 0. So in this world, in Z2, if you multiply anything by 2, the result's 0. So then 2 times A is actually the 0 vector. 2 times C is actually the 0 vector. And then you could just recollect terms this way. This particular equation then tells you 2 things. One is that you only have to push a button once. If you ever push a button twice, you're just undoing what you just did earlier on with that button. So just don't do that. The only thing we can do with the button is either to press it once or just not to press it. But then also there's something else that's really neat. And because the vectors satisfy the property of commutativity, the order the addition is done doesn't matter. That means that once we know what buttons to put, once we know what buttons to push, it doesn't matter the order we do them in, because the commutativity, in the end, the sum of these vectors are the same. So that means that if we want to achieve a certain final light status, starting with a certain initial status, we just need to find scalars, x1, x2, x3, x4, x5, where these are all either 0 or 1, meaning push the button or don't push the button. 0, don't push the button. 1, do push the button. So that the linear combination you see on the left-hand side, which represents us pushing different buttons, will equal the final light status. But again, thinking about our vector operations, what I could then do is I can instead solve this particular linear system that's currently represented as a linear combination, where it's equal to, you'll notice in the original equation that S occurred on the left-hand side. I want you to subtract S. But when you subtract S, that's actually the same as adding S. Just think about it, because S plus S is 0. So then if I just add S on both sides, I get the linear combination has to equal the final light status plus the initial light status. That will then, if I solve that equation, that particular corresponding linear system, that will tell me what buttons to push to go from the initial light status to the final light status. Let me show you what I mean. We'll do numbers now. So in our problem, the initial light status is that B and D were lit. The final light status is that everything's lit. So that's what T is. So S plus T is the vector by using arithmetic modulo 2 would be 1, 0, 1, 0, 1. So I want to find scalars x1, x2, x3, x4, and so on, so that they add up to the vector 1, 0, 1, 0, 1. But that particular linear combination, as we've seen many times, directly corresponds to a particular linear system that has a particular augmented matrix. There it is. Remember now, though, we're going to do all operations modulo 2. There is no division. We multiply by things. And in this case, the only thing we have is 0 or 1. So we either add an equation to another equation, or we just don't do that. We don't do that operation at all. We can swap equations, but we never take multiples of the equations either. We never take a multiple of a row, because we only ever take non-zero multiples of rows. And the only non-zero number we have is 1. Don't multiply things by 1. So then I'll just go and use very limited row operations. In that thing, I will take the second row and add to it the first. That's the result. Next, unlike I normally do in Gauss elimination, I'm going to work on that second row and eliminate zeros beneath it. So then in the second row, it has a leading entry. That'll be the pivot, and I'll get zeros above it and below it. So to do so, I would take R3 and just add 2. I would take R4 and just add 2. And that would then give me this corresponding matrix. Now, still, I'm not quite done. I'll now go and take the 5th row and add to it the 4th row, because they're the same thing. So when you take the 5th row and add to the 4th row, you introduce a row of zeros at the bottom. Finally, I'll then swap the 2nd and the 3rd row so that I get something in at least row echelon form. From here, I could then write down the corresponding system. There it is. And I could go through back substitution. I would just say that x5 will be my free variable, could be anything I want. And I can get all the other variables in terms of that free variable. but honestly, I don't care. I don't want, in this case, all solutions. I just wanted one solution. Since X5 is free, there's actually two solutions to this problem. One where you use the last button and one where you don't. So if we do, suppose we do use the last button, that would mean that I would sign that X5 is 1. Just using back substitution from there will then show you that X1, X3, and X5 are all 1, X2 and X4 are 0. That implies then, if we want all the lights to turn on, we just have to press button 1, 3, and 5 once and only once, and in any order we like. By doing so, we will then turn on the lights on. And I think it's enough for that particular example.